Yeah, that's cool. All right. Well, good morning, everyone. Welcome back. It's good to be with all of you for another round of line integrals. So when we were talking about this yesterday, we used the line integral to find the surface area of a curtain. And then our second example, we were using the line integral to find the work done moving an object or a particle through a vector field. And I wanted to start today by introducing a little bit of notation and then also spending some time on the parameterization before we kind of dive into more complicated examples. When we were together yesterday, as I recall, we ended with this example 2 question. Is this correct? Does this line up? Can somebody confirm that this is where we were when we left off?
Yes.
Okay. Thank you. Okay. So again, the punchline here is that since we were given a function y equals x squared, then we set our we parameterized our curve with r of t equal to t comma t squared. And this was because the t represented our x, and t squared, this would be f of x. And we did this on -2 less than or equal to t less than or equal to 1. And those were coming from the starting and ending x values that were given back in the original statement. Once you have your r of t, then you need to find your dr. And so your dr is going to be 1 and 2t. And then when you actually go to calculate the work, the formula for work would be the line integral of f dot dr. Kind of just a little bit of plug and play. The main thing that I wanted to review in this was the parameterization part. Are there any questions about the parameterization or the finding the differential element part? Very good. All right.
Wait, quick question.
Go ahead, Titus.
Could you scroll up a little bit? Yeah.
Gladly.
Could you scroll up to the previous example? So, cause there's a parabola over here, is this x squared corresponding to the t squared?
Correct. Correct.
Okay.
Yes. You got it?
Yep.
So we're saying that x is equal to t, y is equal to f of x is equal to f of t is equal to t squared. Good?
Got it.
Very good.
Yep.
All right. So one common way to write the work formula is to reference x and y rather than dr or rather than r. And to do this, we recall that our r space curve is equal to x comma y. So this means that r prime is equal to x prime y prime. And so you could think about f dot dr as f, like f comma g dot, here's that same dot that's showing up in both places, dot, and then we have x prime y prime dt, and all this stuff makes up our dr. And so we can do our dot product and notice that we're going to take the x prime and the dt, and we're going to multiply those by the f of x, and that will give us f of x dx, where x prime where dx is equal to x prime of t dt. And then we could also see what happens. We have g times y prime times the dt, and that will give us this second bit over here. Where notice that the dy is, again, let me see if I can write it more clearly this time. Dy is equal to y prime of t dt. So the moral of the story is that we end up with this second version of the work formula. So work is equal to the line integral of f dot dr. It's also equal to the line integral of f dx plus g dy. And in this particular case, we think about dy as being y prime of t dt. We think about the dx as being x prime of t dt. It's just two representations for the same thing. I got a note that said my internet connection is unstable. Do I need to mute my video? Can you hear me okay?
Probably.
Well, I can hear you fine. The video is just a little, like the video is wonky, but
The other mute. Let me go back. Over here. Okay. Questions about this formula? Very good. All right. So when we look at example 3, what I'd like to do in the next few examples is just focus in on the parameterization and not really worry about the evaluation. And so specifically, what I want to point out in the beginning is that we have that we're using this second form of the work formula. So we're using this right-hand version. And so the thing that's in front of the dx, that's going to be the x component of our force field. And the thing that's in front of the dy, that's going to be the y component of our force field. So if you're given an equation that's in this form, you can just simply read off the big F by looking for little f and little g. Okay. So we can see our big F. Our step 1 remains that we need to parametrize C. And in this particular case, notice that C is the circular arc, and specifically it's just in the first quadrant. Okay. So here's that curve C, and so we need to parametrize. What's the radius of this circle?
2.
2. So we'll parametrize with 2 cosine t and 2 sine t. And every time you parametrize, what do you need to remember?
The brackets.
Bracket. I'm digging for something else. Digging for something about t.
what t is between?
Yeah, we need to, if we parameterize, we need to recognize where our t values live or our parameters live. So this would be when our t's are where?
0 to pi over 2.
0 to pi over 2. And in case you're like, where did that come from? Wah-ha. Nicely written there for you already in the solution. So pro tip, if you're trying to check your parameterizations and you're in 2 dimensions, you can always dump things into your Texan friend and just verify that the graphs are coming out the way you want. So step 2 says that we need to find the dr. And now we have this new formula that says that our dr, in this case it's not Dominican Republic, but the differential element, would be equal to dx comma dy. And remember that dx, this would be like x prime of t dt, and dy would be y prime of t dt. So we come up here to back to our r function, and we say, well, here's x of t. It's our first component, and so that tells us that x prime of t would be -2 sine t. And we get y of t is the second component, and so its derivative would be 2 cosine t. And then I just factored out the dt at the end, since it's in common. Questions so far? Very good. So the last step here, and I don't want to work through all of it, but I just want to make sure that you're seeing what's going on, is once you do all of that work, then you substitute and evaluate. So your work integral, which was before a line integral, is now a definite integral from 0 to pi over 2. And we have our function, but now with all the t's substituted in. And then we're dotting it with all of this stuff, which is our dr. And the rest is a bunch of writing. Questions?
How'd you get the equation on the left side? The first part of the dot?
Over here?
Yeah.
Good question. So what I did, I think I got to go up, got to scroll up to be able to see it. So I have that x is equal to 2 cosine. Here's my x's. And y is equal to 2 sine. So for example, this x component of big F would be 2 times 2 cosine.
All right, I get it now.
Times 2 sine. Got it?
Yeah, I got it.
Cool. And then you'll substitute it in. So that would give you the 8 sine t cosine t. Other questions? Very good. All right. So in general, the value of a line integral, the number that comes out the other end, depends on 3 things. Depends on the location of the endpoints of the curve. It depends on the length and the shape of the path. And later in the next section, we're going to talk about times when that path doesn't matter. And then it will also depend upon the direction or the orientation of the curve. We'll talk a little bit about this orientation bit later on today, but the short version being, if you go the opposite direction, you'll get the opposite sign in the work. Here's later on today already. So if you think about what's going on, if we go from A to B, we do a certain amount of work, if we go from B to A, we're traveling the opposite direction, and you would do the opposite amount of work. So here you have some amount of work done, and if we go the opposite direction, we'll end up with some negative work done. And that should line up with things we've done in calculus for quite some time. Yep. One note is that the integration with respect to ds, or the arc length, is a little bit different. But for the most part, ds is going to go away soon. So I'm going to just leave that alone for the moment. Questions? Very good. All right. I'd like to look at the next example using the dot cam. And once again, I'm less concerned about the actual evaluation to a number, and more concerned about the parameterization and the setup, because I think that that's where the struggle will tend to be for you. So let's just focus in on the setup. So first of all, what would be our f in this case?
X squared y?
X squared y, comma,
X.
comma x. So remember, the thing in front of the dx would be the x component of your force field. The thing in front of the dy would be the y component of your force field. And so then when we hit that step 1, which is to parametrize, we now have a triangle, and there's 3 different parts of the triangle. And so we're actually going to have to parametrize 3 different times. And so let's start by parametrizing C1. So maybe I'll call this R1 of T. And so this is moving along the x-axis. The y component is always going to be 0. And then our x component is going to vary. So I'm going to let the x component be my t, the y component be my 0. This will give me the entire x-axis. So we have to also say where our t's live. So where do our t's live in this case?
From 0 to 1.
From 0 to 1. Cool. So that's our C1. So then we go and we want to find C2. Maybe I'll call this R2. And in this case, the x component is fixed at 1. It's a vertical line. And so my x component is going to be 1. My y component is going to vary. So I'll make my y component t, but I have to say where those y's live. So where do those y's, where do these y or t values live?
0 to 2.
0 to 2.
Yeah. And notice that the t above and the t below are different t's, right? Maybe the top one's Earl Grey and the bottom one is Orange Spice. I don't know. But they're different t's.
Wow.
Yeah, that was pretty bad. The T is pretty bad, so I guess that's what you get.
Wow.
Yeah. Maybe I better just stop while I'm still alive. Okay. The third one is the most interesting. So we have a line that's actually doing something, and notice it has a starting point and an ending point. And so the formula that gave you in the book, or in the handout is that you would use 1 minus t times the first point, like the starting point, plus t times whatever the end point is. Boy, I'm running out of paper. So where is my line beginning? What are the coordinates of the starting point?
1, 2.
1, 2. And my line's coming through and it's ending at 0, 0.
0, 0.
Let's just clean that up a little bit to see what we've got. So we're saying that R3 equals 1 minus t times 1, 2 plus 0. And this would be on which t values? Let's check it out. So if we let t equal 0, so if t equals 0, what does this expression evaluate to?
1, 2.
1, 2.
Or
So t equals 0, this would be the starting point. And if t equals 1, this whole thing would evaluate to
2.
1 minus 1.
0.
Yeah, evaluate to 0, which is our ending point. So again, the formula here is that R of t equals 1 minus t, this is like a parenthesis, times the starting point plus t times the ending point, which in this case ended up being 0, 0. So that part just went away. Questions about where our parameterizations for C1, C2, or C3 came from?
Dusty,
Mhm.
did you reiterate where you got the 1 minus t again for the C3?
It's from the formula. I mean, it's something that we've played with in the past, but it's from the formula that's in the notes. Let me see if I can show it. It's right here. It's this formula right here. A line segment that starts with R0 and ends at R1 is given by R of t equals 1 minus t times R0 plus t times R1. And the key is that when you take, if it's equal to 0, you get, when t equals 0, you're going to get 100% of R0, and you're going to get 0% of R1. But when t is equal to 1, you're going to get 1 minus 1, or 0% of R0, and you're going to get 100% of R1. That's where the formula comes from. So it's like a proportionality thing.
Thanks.
No,
So is it
sweat.
always from 0 to 1 for these line segments?
Yeah,
Okay.
if you use this formula, your t's will always go from 0 to 1.
Okay.
I mean,
Awesome.
You could totally have, in this particular case, you could have said, well, your equation was y equals 2x. And so we're going to go R of t equals t comma 2t. But if you did this, you'd have to be a little bit careful because you want to start at the upper point. So then you would say from t equals 1 to t equals 0. Because you had to get the order and the direction correct.
That one makes more sense, like like logically, but I think I get the other one also.
Yeah. They will get you the same result. So this is mathematics. You have freedom, right? You can do whatever makes you feel good, as long as you do it right. Questions? Well, you guys liked that T comment, didn't you? Nice. Okay. Let's go back. Okay, so in this particular case, we parametrized all three curves, and the other thing I wanted to point out here is that you're going to end up with an R1, and that's going to generate a DR1. And then you're going to have an R2, and that's going to give you a DR2. And then you'll have an R3, and that will give you a DR3. And each of these in turn will turn into its own work integral. So it's not difficult, you just sort of have to keep everything straight. I guess it's lines, it makes sense that they'd be straight. So questions about how we would go from those parameterizations to the differential elements to the individual work integrals? Very good. Okay, this next example is not exciting. There's just one new bit here that I want to point out. Specifically, now you have an X and a Y and a Z. In this particular case, the parameterization was given, and so step one is pretty easy. It's like done for you. We just wrote it down. Now, when you come in here and you want to find your DS, it's going to require that you have the derivative of the X component, derivative of the Y component, and then now you have the new and improved derivative of the Z component. When you find your norm or your magnitude, you're going to have that third component there. So the point of this example 5 isn't to do something new. The point is to say, hey, wait a second, if you have 3 variables, then it's the same thing you've done before. It's just now going to have a third variable tacked on the end. The good part about the 3D versions of this is that in the 3D versions, you will almost always be given the parameterizations. And so since parameterization is usually the hardest step, and it's done for you, these are in some ways easier than the 2D versions. Questions? So just a reminder in terms of the formulas, that when you have the DS, you're going to always be replacing that DS with magnitude of R prime of T dt, versus when you have the dr.
That video's getting choppy.
Maybe that'll be set. Oh, I got to share.
Still choppy.
It's probably the best I can do.
It's not just me, is it?
It's pretty much fine for me.
Yeah.
Oh, I think it's.
Oh, it is
I'll
just
be-
you. Yeah. I think.
It's good on my end.
Go drink some tea. So the point being that you have the DS formula versus the DR formula. Neither, they're not, one isn't harder than the other, but they do have a slightly different approach. Questions about ds versus dr or the setup of example 5? Very good. All right, let's work example 6 together on the choppy old duck cam. So the question here is that we want to find the mass of a thin wire if the density is given by rho of xyz equals kz, and it's shaped in the form of a helix with the parametric equation x equals cosine, y equals sine, z equals 2t. All right. And so we're looking for a mass. And so our mass will be equal to the line integral will be equal to the line integral of the density function times ds. Do you remember what ds represents?
Arc length?
Arc length, exactly. So this would be the density per length times the arc length. And so that's why that combination would give you the mass. So thankfully, it's already parametrized for us, so we can jump straight to step 2. And we can look for our ds. So to find ds, we need r prime of t, which is negative sine t cosine t 2, magnitude. I just write this as sine squared plus cosine squared plus 4. Or square root of 5. So this would tell us that ds will be equal to square root of 5 dt. Questions so far?
Is that the density? Is that the same row that we used earlier, like early in the quarter?
This is the row. This is the row that we used when we were finding the centroid. This is not the row that we used when we were finding, when we were doing spherical coordinates.
Okay, thank you.
This is the density row, not the coordinate row. All right, so then we can substitute and integrate. So, see how this is going to work. So our mass is going to equal the integral from 0 to pi of k. The density function was kz, so we'll have k times z, which is 2t, times ds, which is square root of 5 dt. And good news, a whole bunch of constants here. Maybe I'll leave the 2 in place. So antiderivative will be 2t squared, or the mass of the wire will be root 5 k pi squared. Questions about the setup or the integration here?
What does the magnitude of r prime t say? Is that
Oh,
s
here?
squared plus c squared plus
Yeah.
y?
Sine squared plus cosine squared
Oh,
plus
okay.
4. Good?
Yes, thank you.
No problem. Other questions? Very good. All right. So example 7, just pointing out the same thing is happening. Notice that in this case, we're back to that dx, dy, dz notation. And so the thing in front of the dx becomes the x component. The thing in front of the dy becomes the y component. Thing in front of the dz, well, that's the z component of big F. And then because we're in 3D, good news, that means we're going to end up with things parametrized for us. Free bag of tea for anyone. Anybody remember what the name of this particular curve is? So it's t squared, t cubed. Anyone remember what it's called?
Begins with an L, right?
I think it begins with a T. I think it's is it like a twisted cubic? I don't know. We'll have to verify later. Something like that. But the rest of it is just a bunch of writing. So the main part is, do you recognize what your function is? Do you recognize what your R is? You've got your parameterization, you've got your DR, and then you just plug and play. So let's go on and look at one more set of concepts in our last 10 or so minutes of class. So I want to talk about the ideas of circulation and flux. And we can do this in a calculation sense, but I think what we're going to do is we're going to focus on what the pictures do in this particular case. So a number of the forthcoming theorems and results rely on the idea of a closed path or a closed curve. So a closed curve is one whose initial and terminal points are the same. And we're going to talk more about this in the next section, but there's a difference between a closed curve like this, where I start and end at the same point, and a closed curve like this, where I start and end at the same point, but there's an intersection. And so we're going to be focusing in on the really nice, simple closed curves like this one. It's not that we can't apply it to figure eights, but we're going to mostly leave those behind. So in this case, we give the work to move an object around a closed path a new name, and so our new term is circulation. And so you can think about it as its own thing, like a physics quantity, but you could also think about it as a special case of work. So here's the definition. Let F be a continuous vector field, and let C be a closed, smooth, oriented curve in D. We'll talk a little bit about oriented down the road. The circulation of F is circulation, which is the same as work, which is the line integral around the closed path of f dot t ds, where the line integral with the little circle in the middle represents the line integral around a closed path. And so what I want to point out here is that the t, this t here, is telling you that what we care about is the tangential component of the force. So in example 8, we let C be the unit circle with counterclockwise rotation, boom, 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 boom. And then we find the circulation for two different fields. We have the radial flow. And so the radial flow would be this one here on the left. And then we also have the rotation flow, and that would be the one here on the right. And remember that what the circulation cares about is it cares about the tangential component of the force. And so if we look at this first example, as we go all the way around, how much tangential force is there on the path? All your forces are going straight out because it's radial flow.
Should be zero since they're totally normal.
They're totally normal. So in this case, there's no tangential component, and so we would have that our circulation would equal 0. In the other case, where we have rotational flow, and so notice that all those forces are always tangent to the motion. What could you tell me about our circulation? Might not be able to get a number out, but circulation would certainly be not 0. Is that safe? Maybe even maximum.
Yeah, because the entirety of the force is the tangential component.
Exactly. So the dot product and the T and the F are lining up together perfectly. Yeah. So if you work through the details, same thing as before. You parametrize, you find your dr. If you calculate the circulation in the radial flow, what you'll see is you end up with a cosine times a negative sine and a sine times a cosine. So this is minus sine cosine plus sine cosine, hence you get the 0. Versus going the other direction, you have a minus sine times a negative sine times a negative sine and a cosine times a cosine, giving you kind of this maximum possible circular flow in that particular scenario. So the concept of circulation is basically like the work to go around a closed path. Questions about that? Very good. And so, while circulation is a measure of the tangential component of the field along a path, our last concept that we're talking about, flux, is a measure of the normal component of the field along a path. And so here we have an N. And before that we had that T, and that was the unit tangent tangent vector. Do you remember the formula for that unit tangent vector? I didn't comment on it earlier.
Position over magnitude?
Yeah, well, I think it would just be r prime over magnitude of r prime, so it's not quite position, but close. Here, this is not the unit normal vector. I mean, it could be related to it, but in this particular case, N is going to be the unit tangent vector crossed with K. And here, K is equal to the 0, 0, 1 standard basis vector. And we'll have to do a little bit of work to make this all this pull together. Let me show the manipulate so you can see what's going on here. Oops. Okay. In 2D, it's kind of hard to see, but in 3D, I think it's a little bit easier to see that the entire curve, like the path, lives on the XY plane. And so the K vector is standing up from the XY plane. And then your normal vector, notice, is always going to be perpendicular right here to the curve. So this normal vector that we just found, it's going to live on the XY plane, or at least it's parallel to the XY plane, and it's going to be perpendicular to the curve. And the projection of F onto that normal vector in this case would be inward. Sometimes it would be outward. So you can imagine that that normal vector is always going to point exactly perpendicular to the curve.
Dusty. So the normal vector is also perpendicular to the z-axis, right?
Yes, it would be perpendicular to the z-axis.
Got it.
Yeah. So basically what the flux does is the flux tells you how much of the force field is perpendicular to the curve. So it's like it finds the normal part of the field. Part of F, and it adds it up. So work is calculating the tangential component of F. Flux is calculating the normal part of F, or the perpendicular part of F. And so if you just think about this from a graphical standpoint, here, when we go back to that radial scenario, all of these vectors are normal, and so you're going to have an outward flux because things are moving out. But in the rotational world where all the vectors are tangential, then you would have no flux. So here in this case, you have no flux, and you have max circulation. And circulation would be the same as like a special kind of work, if you will. Here you would have no work or circulation. And you would have max flux. That make sense? Very good. I think at the very end, here on the last page, I go through and I derive a formula for flux that I think is going to come up a little bit later. And you can follow along in the notes if you will, if you want to. But this last bit is just the one other formula that you will need from this section. But given that yesterday about this time you had no idea what a line integral is, and today I think every single one of you could start to make headway on the line integrals, I think we did pretty well. So as we wrap up today, looking forward to the weekend. May you all have wonderful days. May there be nice circulation, bringing all of us back together again on Monday for presentations. And may, in the spirit of the craziness of this season, may the flux that's in our lives be minimized. So have a wonderful day, everyone, and I will see all of you in your tea sipping selves next week. Feel free to hang on the line.
Well,
if
have a
you're
good
interested.
weekend, Dusty.
You too. Feel free to hang on the line, folks, if you want to take part in the COVID conversation.
Do you think I could take a
Yeah,
look
Dusty.
at a couple of these examples that we worked through
Mm-hmm.
before we do the COVID stuff? If that's all right.
Sure.
If not,
Totally. Yeah.
Then,
What do you want to see?
example 4. I just want to make sure that I get how that one works, because that one had the 3 DRs. I missed the step 3. What's up, Speedy?
Okay.
Yeah.
Oh. So were
Yeah,
you
this
okay?
one. Okay.
Were you okay with step 1 and step 2?
Yes. Yeah. I just want to make sure that I got this part right. So, okay. So it's the integral of f dr for all of them. Okay. Okay, perfect.
Yeah, so it's the
Cool.
same formula for each one. You just then substitute in the appropriate f, dr, and limits of integration from above.
Okay. And then could I see example 5 real fast?
Yeah. Sure, if you have the question, other people probably do as well.
So we found r prime of t and then the magnitude of it. Okay. Okay. So there's probably some nuance here that was completely over my head. Why are we finding r prime of t and then its magnitude? Because before we were doing f, like the f vector times dot product with dr.
Yep.
And now
Yep.
we're finding ds, which is arc length.
It has to do with the question that's asked. So in this case, we're actually we're asked for ds, which is why I'm finding ds. And this stuff down here is the formula for ds. In the previous question, we were asked for the work.
Okay, so when it
in work, that would be our f dot dr.
It's f dot dr. Okay.
And so sometimes you'd be asked for the work, sometimes you'd be asked for f dot dr, sometimes it would be the line integral of something dx plus something dy. All of these, any of these 3 labels would tell you that down here you want to find dr.
Okay.
Did that answer your question?
Yeah, it did. Okay, perfect.
Cool. What else?
Awesome. I think I'm good.
Cool. Are there other math related questions before we look at the COVID stuff? Very good.